So we're going to start recording. So if that means you want to leave, hey. All right. So here we are with the 4-6 assignment. Woohoo! And we talked about periodic things, and we talked about if things were damped or sinusoidal. So very exciting stuff. So the first thing, we're going to graph the function on -2 pi to 2 pi, so that standard window, and we're going to adjust the vertical window as needed and state whether or not the function appears to be periodic. Okay, so take a look at this. I would need to actually know what the function is. Where is it? Boop, sine of x squared. Apparently I just decided I was going to put a lot of parentheses in there. All right. So on our window, which is where you get to choose how far left and right and up and down you go, we're going to put -2 pi and then 2 pi. And I doubt that I'm going to go by ones because that would be weird. So I'm going to go by pi over, what, 4? Is that in the middle of 2? Okay. So we'll go by pi over 4. And then my y minimum and maximum, I am going to just center around 3 or so. I don't know that it does much else than that. And then all this stuff is extra. You want to make sure in your modes that you're in radian mode. Otherwise, it'll start graphing in degrees, but you've only gone up to like 6 in degrees. So it's really going to have absolutely nothing there. So if we look at the graph of this, ooh, very exciting. And since I'm on a computer, I'm going to be fancy and just take the image of that. Where did it go? That is what it looks like. And now I don't know where my, oh, there it is, went. Okay. So if we take a look at that and we look at the definition of periodic, periodic says if there is a positive number c such that if you plug in a c, it's still the function, you get a periodic function. So this is not a periodic function, this is not, and this is, which is funny because that looks exactly like what we just got, just a little bit wider. So this one we get to type out is periodic. Huh, perfect. All right, again, because it's going to never have like a different distance between the peaks. So, all right. The next one here is x squared plus 2 sine x. So going back to our calculator, or Desmos if you feel like it. But again, if you don't practice with the calculator, it's going to be very hard to use it when that's the only tool you get on certain tests. So x squared plus 2 sine of x, bloop, is going to have the same window, so we'll see how that goes. Oh, and that looks like nothing helpful, unless it's so big that it's periodic later on. So maybe I'll change my window to a little bit taller, just to see if we can see if it does come back down again somehow, just later on. Yeah, no. So in that case, we're going to say that is not periodic, because the equation here being added to it actually kind of makes that not happen. So it's all based on the composition of that. Why is that not letting me make it smaller? There we go. And so we will say it is not periodic. I was wondering if maybe it's just so large that it became periodic by going like, you know, this, and it was kind of like off the screen or something. But by going bigger from being up at 3, it doesn't seem to be happening. All right, so we were foiled in those efforts. Sweet. Now we're going to do the next one, x cosine x. So we go to y equals and do x cosine x being multiplied by each other. And oops, oh, delete goes backwards. Let's just do it all over again. X cosine x, and yeah, they're being multiplied. I'm going to change my window back to -3 to 3 because that's a little bit too tall to see nice patterns. So, all right, wow, okay, so that one, especially if we look at the notes, actually kind of starts to look like that one, which we've already said is not periodic. It doesn't repeat itself over and over again. It only sort of does. So on that one, again, I'll just give an image so that I understand why I'm saying not periodic. It's going to be over here. And I'm going to do this guy. Okay. Then the next one is, wow, that's kind of a funky equation. All right, and yeah, 3. So if we go to our y equals, we're going to do parentheses sine of x plus 1. I assume it's supposed to be all. That's an interesting idea. I wonder if they want it to be x plus 1 cubed, or if they want the x plus 1 inside of here. Well, I choose this one, and so then I'm going to do cubed. We'll end up doing both, just because I have time. Whoa. Is that periodic? Yeah, it just repeats that very strange moment the entire time. What if we changed it, like I was saying, to a parenthesis here? I probably don't have enough parentheses now. Delete that one. That one ends up being periodic anyway, so it's all good. I'm going to go up farther, though. Whoa, that is a freaky bow that it's got in there. All right. So it turns out that both of those work. So we'll put them both in there, and we might end up typing why we had an issue. And so I'm going to write, is it like this? Question mark. Or was it like this? With an extra. Because now I forget which one is which. This one is that one, and this one was that one. All right. Anyway, so that's fun. So as I take a look at all of this, Carl or Duncan, any questions on those, or forever hold your peace? Okay. All righty. So this next one here, it is oscillating between two parallel lines. So we're going to find some equations of those lines and graph the lines and function in the same viewing window. Ooh. All right, so we're going to graph this guy and kind of see what it looks like. Sorry. So in our y equals, we're going to put 2x plus cosine x. All right, so my window is going to 10 now, so maybe we'll just change it back to 3. Oh gosh, that's really not helpful. Maybe negative 10 to 10 would work. Sort of. I was looking at it on my own calculator, and I don't know what the window was, but it was clearly bigger than that. Okay. Well, anyway, you can hopefully see that it oscillates here just a little bit. It's very wide. And the interesting part is that it's oscillating kind of on a cosine, but because of this 2x. So it turns out that 2x is actually, if we graph it at the same time, like the middle of the oscillation. And so it looks like it's like shifted up a little bit and down a little bit from there. In fact, if we're talking about cosine, its height is 1, right? So I wonder if we took our equation and graphed 2x plus 1 to shift it up and 2x minus 1 to shift it down, and see if that surrounds it. All right, and so you can see that it just barely touches right up here and barely touches down there, and that's because of this 2x. So if I take a picture of this, since that's what's happening, and then I take a picture of this, and of course if we were not on the computer, you would have just sketched the graph, which just means it could be kind of sloppy if it needed to be, but you would want to label as much as possible so that it wouldn't be hard to understand what it was referencing. All right, and so now we see that all of these equations have to do with this idea. And again, that's because the center of the oscillation of the cosine was at 2x because of the way that the equation is written. So it's good to know. Yeah. All right, so then the next ones here, we are talking about, is this sinusoidal or not? We don't necessarily have to graph all of them because the whole idea of, at least from our notes here, was that sinusoidal functions can be written as a sine. So one of the pieces was that the same period is in both of them. So we understood that inside this sine and inside this cosine, they both had an x. Inside these cosines, and sines, they had the same 3/7 x, versus these ones that didn't have matching inner parts there. So if we take a look at this, all we're looking for is if those inner parts are the same. So this one has an x, inner part same. Inner part is same there, same there, same there. Different, 2x and x, so this one is not sinusoidal. And then the last one has 3x and 2x, so it's also not sinusoidal. This is quite a word. Okay. And again, all the rest of them are, because everything that is being taken into the cosine or the sine or the tangent. Actually, now that I'm thinking about it, I don't think tangent is going to make it sinusoidal, because you cannot write tangent as sine or cosine. Darn. But we can go ahead and graph that one just for funsies and see what happened, because tangent is not sinusoidal. It's that weird kind of cubic looking function repeating itself. So if we go in here and just kind of clarify, at least for this one here where we were maybe unsure, we've got 2 sine of x minus tangent of x. And if we graph, yeah, that is certainly not a version of sine that I've ever seen. So that's not going to happen. But just so that we kind of understand what was happening, the other one, 2 cosine of pi x, and ending plus sine pi of x. It's funny that that x is so much more capital than that pi. Anyway, if we graph that, clearly very sinusoidal. It could be sine just shifted. So there we go. So I guess I'm going to type that so that we all know that those ones are sinusoidal. Beep. All right. And then our last examples, yep, this is it. So that's why this is not taking so long, are the damping ones, which are kind of cool because they're just sandwiched between 2 equations. So if we take a look at this one, it turns out, because of the way that it's written, I already know that it's going to be damped by this e to the negative x. So we're going to have this oscillating sine function kind of going in the shape of e to the negative x. So for a nice visual, we'll go ahead and graph. So e to the negative x, where's my e? To the negative x. Don't forget to use a negative sign and not a minus sign. And then sine of 3x. Oops. Oh yeah, there it is. Okay, so it's kind of doing this giant thing, and then it kind of comes down here, and that's because e to the x is right here and kind of squashes it. So we've got e to the negative x, and so if we graph that one, you can see that it just touches the top of it. Down here, that's going to be the one flipped across the axis, right across the x-axis. So that means that it's negative of the previous one. So negative of e to the negative x, because we want it to flip over the axis. So that one's going to be underneath. So what does it say that it wants? If so, identify the damping factor and tell whether the damping occurs. Ooh, interesting. Okay. So our damping factor is going to be e to the negative x. And of course, I suppose I can type it like that on here. Don't I have an x? Yeah, I do. There it is. Okay. And then tell whether it occurs as x goes to 0 or as x goes to infinity. So taking a look, x going to 0 means that it would damp it here, but it doesn't. It continues on to infinity. So in that case, we're going to try as x goes on to infinity. So without having to type that, I'll take an image of it. So many windows open. There it is. Okay. Sweet. So then our next one is x sine 4x. And just as we looked at this one, it's probably this multiplier that ends up damping it. And so I already know that it's going to be damped at y equals x. So just that diagonal line. But just so that we can see it, we've got x sine 4x. And that's too many parentheses. And then we'll graph x at the same time. And negative x, why not? All right, so there it is. And so it's saying, is it squashing at 0 or is it squashing towards infinity? And it's definitely squashing at 0, or what we call damping. I just decided to say squashing. So that means that our damping factor is x, the equation, and then it's going to go as x goes to 0. So however it is that I want to do that. This is how I make things invisible on when I make documents. Ha! Okay. And then a 0. Rather than doing that whole screenshot thing. Oh, D-O. Alrighty. So the next one has an equation, of just a number being multiplied. And we noticed that in here, when we had just a number, even if it was a square root number, it doesn't actually make it damp. It's just creating a different altitude. And so this one is not going to be doing that, so we don't necessarily need to graph it and look at it. So we're going to say it does not exhibit damping. Good to know. All right. Then the next one is also just another number, even though it's pi squared. You might think, oh, but that's different. No, pi squared is just a number, so that's not going to damp. This one here is going to damp between negative x cubed and x cubed. So again, if you're interested in seeing that, you could insert in a cube. And was that sine of 5x? So you can kind of see, woo. It's also nice to graph because then we can talk about if it's going to damp at 0 or if it damps towards infinity. So this one clearly damps at 0. Oops. I want these. There it is. And then our damping factor is actually x cubed in this one. What is it that squashes it? And then this one here, it looks like it might be a number times it, but it's a number to the x. So it's an exponential equation. So it does have a damping factor, and that damping factor is at 2/3 x. And then if we look at our visual of what it might look like, we've got 2/3 to the x, and that's going to be multiplied by sine of 2x over 3. And so if we graph that one, whoa, that is the very large period that's happening there. So either way, it is definitely going towards 0 because it's not expanding again after 0. So this one, towards infinity because it's not expanding after 0. So that's it. Oh my gosh, what a short assignment. So hopefully that worked out for everybody. I don't know. I'm going to post this to YouTube for all to enjoy. As long as I can figure out how to, there we go. Stop.